All right, so the objectives for today, we're starting to talk about pressure. So we'll define pressure and its variation with depth, and then we'll calculate what the pressure is at various heights. Let's just first dive right into the equation. So the basic fundamental equation for pressure is just some force over an area. The units are Newton per meter squared, which is a Pascal. It's the other name for it. 1 bar is another unit, is bar, is 10 to the 5 pascals, which is 0.1 megapascal and 100 kilopascals. ATM is another unit, atmospheres. So if someone says, okay, it's 1 atmosphere, that's actually what standard conditions are. So 101,325 pascals. So a lot of this is SI and kind of weird. And then you could also have pound force over inch squared, which is sometimes you see as PSI. Okay? So there's a lot of different units we use for pressure, and you just kind of have to be aware. So really all pressure is just a force over an area. So as long as you know the force you're applying over some area, then you know the pressure. What is pressure really? Well, in this room you have gas molecules of air bouncing around hitting the walls. Okay, because gas spreads out on the floors. Okay, and the force that they hit over that area that they hit, that's kind of the pressure that they're exerting. Okay. That's kind of the fundamental concept of pressure. Pressure is always a normal force acting on a body. Okay, so what does that mean? Well, here's 2 people, a small person and a big person. Oh yeah, SPI, whatever that is. Thank you. So just say, we'll get to more details here. But say this person is providing 3 psi of pressure, and this one is 6 psi of pressure. All right, and again, that kind of means if you had a 1-inch cube of area, okay, so you multiplied each one by 1-inch cubed, then this is 3 pounds, and then that would be 6 pounds pushing down. And the force is always normal, like perpendicular to the surface. All right, so later on, when we start talking about dams, say there's water, you're going to have a hydrostatic force, which is due to the pressure, which is going to be perpendicular to that surface. Okay? So say the dam was angled. Which way do you think now the force is going to act over here? It's going to be angled perpendicular. It's going to be something like that, where that makes it 90 degrees, slightly cockeyed, but it's going to be perfect 90 degrees to that. So pressure is always going to be a normal force. That's just how we define it. Okay? All right. How can we walk on snow? Just for future reference. And you'll have a practice problem on this. So we're going to take 2 cases. So the one on the left is we're just walking on our feet. So we have a big area, okay? I just did one because it's easier. How many, what's the force? Oh, sorry, the pressure. Thank you. Yep. 100 pascals. Yep. What about over here now? We make our area bigger. 50 pascals. So that's why we can kind of walk on snow. All right, because this area is bigger, you're providing a less pressure. Same goes with when you're cleaning. I do a lot of cleaning fish when I catch them. I make sure my knife is sharp. What happens when you sharpen a knife?
Increase the area.
Yeah, you make the tip of that knife smaller. You're making the area smaller. So if you apply the same amount of force, it's going to be a higher pressure, right? The area is so much smaller, you can penetrate easily. Okay. Absolute versus gauge. So sometimes you'll see pressure given in Pascal, but it's gauge. It'll say gauge pressure is blah, blah, blah. So you have to actually figure out the absolute pressure, which is pascals, and you subtract it with atmosphere. Okay? So your tire pressure in your tire on your vehicle, that little meter that you plug in is actually measuring gauge pressure. So to actually find the complete true pressure inside your tires, you'd have to add what the atmospheric pressure is. Okay, so I don't know if you knew that. But the pressures you use for your tire are in gauge, so you have to convert that. All right. So you'll do a practice problem with that. There's also sometimes vacuum pressures, which just means that the pressure is lower than atmospheric pressure at that case. So this is vacuum pressure. All right. Questions so far? All right, now let's look at pressure. Oops. Red. Variation. Oops. With depth. Say we have a tank filled with water. What do you think happens as you go down in the water? Pressure increases, yeah. Okay, and the way to think about it is there's more weight of water as you go down. There's more force pushing on you over the same areas. Pressure increases. So in order to find the pressure, I'll tell you about that symbol in a minute. Is say we wanted to find this bottom pressure, which is I'm going to call PB. So PB, bottom pressure. It equals the top pressure plus rho GH. So this is the density of your fluid. This is acceleration due to gravity. And then this is your height. So you can label that on here H. So anytime you want to know what your pressure is, as long as you know the density of the fluid you're in and the height you are, then you know your pressure. Okay? And as you notice, you're going to have another graph on the new homework. You're going to plot the pressure on a submarine as a function of height. What is that going to look like as a trend? Say that again? Linear, yes. Thank you, yes. You will see a linear line because h is only to the power of 1. Good, good. Yep. Good. Okay. Questions? Remember that. Drill that right in your head. Bottom pressure equals top pressure plus rho GH. This symbol, this little triangle symbol up there, that's just reference to the top part of the liquid line. And typically, that's atmospheric pressure. Okay. So here's just a quick sketch. You have water, and then this little black section from B down to C is oil or whatever, something else, mixture of something. The biggest thing you got to watch out when you want to find the pressure is the pressure at C and E the same? No. Even though they're the same height, it has a different density, different fluid there. So what I would do is figure out what the pressure is here, and then redo it to figure out what the pressure is there. Okay? So just watch out for that. So A and B are at the same pressure. C and E are not. And D is the smallest, right? Let's talk about Pascal's law. Yeah. Yep. So he was saying, so if you wanted to find the pressure at C, it's atmospheric pressure, which is the top, plus rho GH, and this is of the water, plus rho GH of whatever that black fluid is. Yep. Bless you. Might as well put this in here. Go ahead and write that, and we'll talk about it. Then we'll get to the practice problems. Okay, so Pascal's law basically states that the pressure applied to a confined fluid increases the pressure throughout by the same amount. So for example, say these two pistons are at the same level. The easiest way to think about this is initially thinking about that first. And this area over here is 1 meter squared, and this one's twice the size. If we apply a force of 100 newtons over there, all right, that equates to 100 Pascal of pressure, which applies at the same level, same liquid, the same pressure there. Okay, therefore, we now have 200 newtons of force going up. Okay, so this is how they use to lift cars, hydraulics, whatever. Okay, and in fluid power, this is kind of the stuff that you're going to really focus on, is learning how to do some of that. Okay, so that's Pascal's law, very, very important, and they use it a lot. All right, questions